It's exactly 2:00 p.m. Very welcome to today's webinar, Accelerating Electric Motor Design with ANSYS Motor CAD, hosted by our Dutch scaled-up Lightyear, by Chris Foster, and Infinite Simulation Systems by my colleagues Tim Lin and Edwin Wustmeijer. The duration of this webinar will about 1 hour be extended. And just to give you a quick view to the next slide, it's about the introduction of GoToWebinar, just a small introduction about this. Some few items. We have taken a screenshot of your example for you as an interface. You should see something like this on your desktop or laptop in the upper right corner. By clicking on the red arrow right above, you can unfold this little screen and choose your audio modes and questions. You are listening in using your computer speaker systems by the default, and if you would prefer to join over the phone, just select telephone in the audio pane and the dial-in information will be displayed. You will have opportunity to submit the text questions or chats during this webinar. At the end of the webinar, we collect these questions and chats and will give you answers, as many as possible, within the hour. And during the webinar, you are automatically muted. And this webinar will be recorded and sent to you as soon as possible. So the speakers for today are Chris Foster, Lightyear, graduate electoral engineer and responsible for motor design. A colleague Edwin Wustmeijer, senior account manager, graduate engineer and responsible for sales. Then Tim Lim, application engineer, graduate electric engineer and responsible for mechanical and electronic support matters. Then the agenda for today, first of all, an introduction by Edwin, then the electric motor design workflow accelerated with the simulations insight by Tim, then Lightyear motor CAD use cases by Chris, and of course, finally, the questions and answers. I will now give the stage to you, Edwin, so that you can go further with the slides. Good luck and enjoy, everybody.
Thank you, Anna, for the introduction. Yeah, once again, welcome everybody for joining the webinar, and special thanks to Chris Foster for presenting a case from Lightyear. I will give a brief introduction. First of all, a short introduction on Infinite. Since the beginning of 2020, we are part of the 4ITGO group. And that group contains the companies CAD Corner, GPO Solutions, and Infinite Simulation Systems. I will put on my camera also. Next slide, please. The team contains 51 team members, and yeah, we are dealing with more than 750 customers in the Benelux. Part of that team is the PTC partner, GPO CAD Corner, and the channel for CG Tech. And of course, ANSYS Infinite as ANSYS Elite partner. As Infinite, we are for 30 years on the market now, and ANSYS itself exists for 50 years, so that's a long time. And we are a solution partner to enhance your product development and product process from early concept design till manufactured products. Next slide, please. Our customers are active in all kinds of industries, in the mechatronics, oil and gas, automotive, and this is some of our customers. Next slide, please. If you look nowadays at simulation, we have specific solutions for from simulation from ideation to operations and beyond. And what do we mean with that? in your ID phase, in your conceptual phase, you have to make design decisions, and that can be the geometry, your materials, and we have tools for that to make that quite easy. And then you can compare if one design is better than the other, but not with absolute values. Then you go to the next step, that's the designing more in detail, with the final goal to reduce your development time, but also to get a better insight on your product, and of course a higher quality. But it doesn't stop there. Next thing you can do with ANSYS is simulating the manufacturing process by, for instance, reducing weight using topology optimization, but also regarding to 3D printing, simulating your printing process. So do you get out the shape you want out of your printer, which you had in mind? The next stage is the operations, and nowadays called more like digital twin. So that means you can build a digital twin of your total system and use real values for loading from out the process you are measuring with sensored data. Next slide, please. This is an example of such a digital twin. For instance, first of all, you are looking only to your components separately, and you can use field simulation or analytical models like fluid mechanical and Maxwell solutions. But if you look more closely, then you can build from those different components one system which represents reality. And that's called the twin builder. So you use real data and you connect different components in a system, so you get a total overview of your system. Next slide, please. If you look at ANSYS, ANSYS is on the market for 50 years, started more like mechanical, but over the years we have a lot of additional functionality. And those are, of course, different physics. One of them is fluids, and the products are fluid and, for instance, CFX. Then the structures for your mechanical simulations, electromagnetics, that's what we are dealing with today. Part of electromagnetics is, for instance, Maxwell and Motor CAD. Semiconductors, that's more for designing chips. Mission critical embedded software for safety questions, and finally optical solutions. And of course all those systems make use of materials, so we have Granta as a material information system, and everything is built on one platform, and that makes it possible that you can use the results from different physics together and make a multiphysics model out of it. Next slide, please. If we look more into detail in electrical machines, then there is a need for design, analysis and validation. And most of the time, electrical machine contains complex areas of physics. And you want to have a better understanding, and that's why you perform the simulation to get compliant with the performance targets. But those physics are combined, of course, and they give you the most valuable information. So you have to couple those, and for instance, then you can investigate the cooling, but also noise, vibration and harshness. And your final goal is, of course, to reduce prototypes, but also to give you a better insight information, because at a simulation model, you can look more inside the model, what's happening at different locations, which is not possible with prototyping. Next slide, please. Can you click again, Anna? If you look at Motor CAD and ANSYS together, they offer a complete end-to-end workflow for your electrical machine design. Click again, Anna. As that it in your total design process, you can look at your size design, your develop and your validation, and that can be done with all in the same environment and platform with ANSYS and Motor CAD. To to finally get less prototypes, look at more complex systems, and also have data and process management at any stage. So thank you for your attendance, and now I will pass the word over to Tim Lin, and he will go more in depth into the Motor CAD solution. Oh yeah, my final slide. Motor CAD is used at many companies nowadays and growing, and of course mostly for electrical motor design. Tim, can you take over?
So Tim, it's the stage is for yours. Can you see the next slides?
Yes, thank you, thank you, Edwin. Thank you, Edna. Let me see if I can move on.
Do you have control of the mouse? I'm sorry.
Yes, I do.
Yes.
Okay, great.
Thank
so,
you. Thank you.
Thank you, everybody. So just move on to focus a little bit on what's Motor CAD and what can we expect from it. So basically, when we are trying to design a motor, I believe some of you has experience, some of you may have heard of it, that it is actually a very, very challenging topic. Motor itself, electric motor itself exists for more than 100 years, but it's still evolving today. And you see that there's so many issues that we have to encounter, we have to solve. There, you want to higher power density, higher efficiency, but in the meantime, you want to control the thermal reliability, reduce the noise for EV applications, reduce the size, the weight in general, especially important for EV applications, and then also the overall system efficiency. That on top of this engineering challenges, what we'll also see is the time to market. You want to be faster than your competitor, reduce the production cost, reduce your the design time and also the design cost, and even to reduce and prevent from extra cost after operation and implementation. So all of the things comes together, becomes a very challenging topic, and that's why Motor CAD is also is one of the main tool to tackle with all these challenges. So now if we look at Motor CAD, what it offers is a rapid multiphysics design tool to help you to tackle with all the challenges we just mentioned in the early phase of the design of your design flow. Now, if you look at the position of Motor CAD in the entire ANSYS motor design portfolio, it is positioned as an early design phase. So let's say when you have the design requirement, when you have the engineering limitation or specification as a starting point, and when you try to do some motor sizing, then this is where you start with Motor CAD to try to find out which type of motor is suitable, and also try to find out if you have a certain constraint in size and weight, and how are you going to design the most powerful motor or most efficient motor you can through Motor CAD. Especially you can do this usually within a couple of days to be able to find out the final solution before for your motor design. And then if necessary, you can dive into the high fidelity FEM solver. ANSYS provide Maxwell for electromagnetics, and also mechanical or other CFD tools for NVH and cooling problems. So eventually everything comes together as a system, and then you can also include in system level in the early stage of your design. So Motor CAD contains 4 modules. There's EMAG for electromagnetization. There's a THERM for thermal analysis, MAG for mechanical analysis, and then a lab module for running the efficiency and also to understand the performance to go across a certain drive cycle or a duty cycle. So it's really gives you a rapid and accurate electromagnetic, thermal, and mechanical analysis to be able to consider all different physics, not just multiple physics, but multi-physics. That means it's correlation between them in the early stage of your design. So in Motor CAD, it's a template-based design tool. So basically what you have is all kinds of different typical types of radial flux rotating electric machine. So there's only a rotating electric machine up until now, and also only radial flux. So axial flux is not included yet. The motor type that we're looking at is brushless. There's basically all the typical types: brushless permanent magnets, induction, synchronous reluctance, all kind of typical radial flux rotating no electric machine. That's what you can find from motor cards. And then there's in electromagnetics, of course, there's a 2D FEA solver to solve a very precise electromagnetic field. And then on top of that, there's also electromagnetic force that you'll be able to obtain from the rotating machine to see how your force is distributed across different tooth. And also, for instance, the Koch torque or the torque ripple as a whole that you can also quickly check. Now, typically using a finite element solver, this requires maybe a few minutes for 2D solvers, or sometimes could be seconds. It depends on how much you are solving. But the benefit is that you don't have to combine with the 3D FEA analysis to get the full machine operating performance, because motor CAD also combine with analytical solutions together to take into account of this edge effect at the two ends or the entire 3D performance. So that's why you can get a full machine performance very quick. So it's not just a 2D solver. And also you can see that the phasor diagram, equivalent circuits, you can play with your winding layout and also get the harmonic response. Now, one of the strong points of motor CAD is the multiphysics coupling. So you can use the loss, EM loss, as the accurate input for your thermal analysis, and use the temperature distribution across the entire machine as the accurate input as your temperature dependent EM properties. So eventually you will be able to quickly iterate to converge the solution. And the converged solution, usually you'll be able to get a nice converged solution within 10 minutes. So this is some more detailed capability of the FEA solver inside motor CAD, not just the detailed EM force and also the BH field distribution, but also you can do a AC winding loss inside motor CAD, and you can even bring in your own DXF customized geometry into motor CAD, so that maybe you are changing something slightly at a different corner or a different bent dots, then this can also be taken into account. So the thermal module is one of the most prestigious model in motor CAD. It has been developed for more than 20 years, and then there's a lot of experience being built in. What it does is basically it use the geometry and then to convert it into a lumped thermal network, so that eventually what the solver is solving is this net circuit, is thermal circuit or thermal network. That's why it can give you the result also within seconds. But of course, to be able to do so, that relies on years of experience on all the different types of empirical testing and also calibration to be able to generate an accurate enough thermal network that allows you to skip the time-consuming CFD or FEA analysis for thermal analysis. And it includes a wide variation of all different types of cooling, cooling techniques. So, for instance, not just natural convection, forced convection, but also through ventilation, water jackets, and even spray cooling for your end windings. So, as the new cooling techniques are keep introduced into the industry, motor CAD is also keep including them in the thermal analysis, so that you can use the accurate cooling type for your own design. Now in thermal network, it can take into account of the arrangement of your windings, and also you see that the thermal resistant network, what it looks actually in the solver. Also, if you want to change something to your design, and then that's not included in the template, you can also customize the thermal network yourself. So just change the circuit as a to your own design for a more accurate output. The other thing that's very, very great to have is the manufacturing data, which includes what kind of manufacturing process to have a more proper input to your thermal conductivity or heat transfer coefficients. So for instance, you can see that while the gap is changing only slightly, we see that the huge change of the thermal resistance. And so this is actually very important that you need to take into account. And using this very pragmatic table, you'll be able to just quickly select what's the more appropriate thermal resistance for your interfaces. And of course, you do have the freedom to manually type in your own interface thermal transfer coefficient. So the lab module is another powerful tool from Motor CAD. It allows you to quickly get the this efficiency map, and also you can feed in a drive cycle. Maybe it could be your own drive cycle. It also from a standard, there's a multiple standard included, so that you can just try to see like how your motor is going to perform across the entire drive cycle. And how it works is basically build a model by sweeping the FEA analysis in a certain density across the entire operating space. So say your operating space from 0 rotation to all the way to certain RPM, and then you have also the current input, or you can be also a voltage input, and then what's your maximum motor current? Maybe you want to limit that, and also just set some certain number of sweeping points. Then eventually it gives you a entire model based on the response surface of the sweeping points. So one important thing is that you will get benefit from this lab module, and together with the coupling between thermal analysis and electromagnetic analysis, is that you can actually see what's your continuous performance, continuous working performance, instead of your peak working performance. So for a PM model, for a PM motor, maybe you have this nice high torque peak working performance. However, because you want to limit your temperature of your magnets so that it maybe not exceed, for instance, 120 or 140 degrees Celsius, then that means it cannot continuously output this torque, and it has to depend on your thermal dissipation design. So eventually, the Motor CAD helps you to determine what will be the actual continuous output of your motor design. And as you can see now, it becomes maybe like a 20% less of the torque, and also the entire curve become a little bit more flat, because you don't at this knee points now you also have to consider the thermal effects. The drive cycle is also specifically useful for EV applications, but you can also bring your own duty cycle for different applications for sure. Now, all kinds of international standards are included, so that you don't have to bring those standards by yourself. You can just use directly those standards inside the Motor CAD. Mechanical analysis is a quick tool to evaluate whether your stress has gone beyond maybe elastic region, so that you want to control the stress maybe within a certain range so that the motor does not deform. Usually you would like to do this when you have this IPM machine and very thin precision. Some locations you have very thin geometry. Then you want to make sure that they don't go under high stress. So this is also something that you would like to take into account in the early stage of the motor design. And the motor CAD is primarily used by electric machine designers, but not just focused on electromagnetics, but focused on the entire physics domains. So from electromagnetics to thermal to mechanical and also the drive cycles, it is very powerful for you starting from the sizing and then all the way to a detailed analysis. And then if you want to have more high fidelity advanced material model with very detailed insights, then you can easily transfer this motor CAD model into ANSYS Maxwell. There's also an automatic script for you to just automatically generate everything in Maxwell. So you don't have to build everything from scratch again by yourself. And then you can also export the reduced order model, immediately use the motor CAD model inside a system simulation. So either you are using Twin Builder, or you might also using some other system simulation tool, for instance, like a Simulink from MATLAB. Those are all already available for motor CAD to export the reduced order model. It's also very powerful to when you are even in your testing phase. Then you maybe want to check the inside of the motor, and then also to do some validations. It is also a great tool to use motor CAD alongside with the testing. So the system simulation in motor CAD, you do not have the system simulation. So the system simulation is more for you to export this functional mockup into Twin Builder or into a Simulink for system simulation. But of course, even though there's no really system simulation in motor CAD, there is indeed the efficiencies map and also the drive cycle, which is also part of the important factor for you to consider as a system engineer. So the functional mockup is very powerful. I'm not sure like how much detail you can see. As you can see that there are almost 100 inputs for you to be able to control, and also tens of outputs, so for you to monitor. So this is very, very powerful functional mockup for you to run the entire model in system simulation. And as I mentioned, to export into Maxwell is very easily. So all the way from here, just a few clicks, then it will automatically create the entire model and also the boundary conditions, the inputs for you automatically inside Maxwell. Now, for you who are not familiar with Maxwell, Maxwell is an advanced electromagnetic FEA solver provided by ANSYS. And then it includes all kinds of high-end material simulation capability, also together with powerful HPC capability to really speed up your simulation. And then it works very nicely together with all kinds of system simulation and also reduced order model. So this is the flagship product for electromagnetics provided by ANSYS. And important advanced material modeling for motor is you can simulate the demagnetization, even to consider a recoil curve, so that you can not only see it gets demagnetized, but also to see how much the remnant magnetic field it is inside your magnets. You can include multiple core losses, even anisotropic core losses, even temperature dependent anisotropic core losses. So that's like very high fidelity advanced material model you can include. You can also include magnetostriction, the behavior between your magnetic field and also and the mechanical stress, and also the inverse magnetostriction to take into account the deformation and stress caused by the electromagnetic field. And of course, in Motor CAD, we have this lump model, lump parameter thermal networks, to quickly run the simulation. But if you want to calibrate with a more high fidelity CFD solver, that's also possible. So that's also a typical workflow that people will use Motor CAD with. In this way, you first run the thermal analysis in Motor CAD, get a rough result. You can export the geometry from Motor CAD directly into ANSYS Design Modeler, and then bring it into Fluent and to run this full simulation. After the simulation, trying to calibrate the heat transfer coefficient or your thermal resistance and conductance, so that you can get also the accurate result in Motor CAD and maybe use it later on in your drive cycle analysis. So to quickly sum up, we can use simulation to really help us to decide the design specification, to include the advanced magnetic analysis, to get a torque, speed, efficiency map, to also include thermal analysis, so that it's no longer like first electromagnetic, then thermal, but you can have the multiple physics analysis together, and then MVH and structural integrity, and eventually system integration. And the good thing to leverage simulation in your workflow is that it gives you overall 12% of better performance, and then the most important, to reduce your design cycle by up to 16 times, and also to reduce your overall cost by 20%. These are quantitative benefits that you can get from using simulation. So that's the end of my slides. Once again, thank you everybody for joining. This is the Motor CAD together with Motor Design.
Okay, Tim, thank you very much. I'll give now the stage to Chris Foster, Motor Electric Design Engineer by Lightyear. Chris, the stage is for you.
Thank you, Anna. Good afternoon, everybody. I'm glad that you are still sticking around to find a bit more about Lightyear as well as about Motor CAD. So I quickly wanted to use this opportunity to first tell you a bit more about Lightyear, or what we're doing, and then why are we using Motor CAD. So at Lightyear, we are a company based in the Netherlands, in Helmond specifically, and we set out to design solar electric vehicles, and that's also what we currently keep ourselves busy with. And the vision of Lightyear is clean mobility for everyone, everywhere. And that's the ethos that drives us to develop this technology. So one of the things that we want to achieve as a company is the adoption of electrical cars. So what is hindering, for the reason that we want to accelerate clean mobility throughout the globe. So it's a very bold vision, but that's ultimately what we're working towards. So what we set out to do is to first figure out, why are people not buying electrical cars, or why is the adoption rate so low? So there are numerous factors, and one of the things that we realized, that if you actually want to increase the adoption rate of electrical cars, you would need to upgrade the whole infrastructure, your power plants, grid, the charging infrastructure itself, and then in the end replace all of the cars. So we asked ourselves, is there not a more simple way to actually do this, and to leapfrog the whole system to actually integrate it into the car itself. So that was one of our questions. The second thing that we set out to do is to see what are the most widely available energy sources. For example, in this case, which I'm showing here, is sunlight. So this is a picture of the solar irradiation of the sun, obviously, across the globe. And the second thing is normal wall outlets. So we asked ourselves, how can we integrate into the car a system that would be able to utilize those two energy sources? So we sat down and started thinking exactly how can we utilize the power of the sun more. So one of our design choices are to maximize the area of the solar panel on top of our car, so that we can ultimately generate enough energy from that. So one of our design choices are to actually put solar panels on the car. The second thing we did is we made sure that we designed a vehicle that is a low mass, and thirdly, that is very aerodynamic. So to reduce your aerodynamic losses, your drag losses, as well as making sure that the mass, you don't have any unnecessary mass you're carrying around. And the fourth thing we did is to actually set out to design the most power efficient or energy efficient powertrain to date. And one of our design choices are to use in-wheel motors, and that's why we are also using Motor CAD in our design as one of our design tools. So to move on, if you go for lightweight, large solar area, low aerodynamics, and low mass, this is ultimately what you end up with. A beautifully crafted car or vehicle, ultimately designed to accelerate the adoption of e-mobility or clean mobility. And as I said, what I wanted to elaborate more on today is the in-wheel motors. So we from our design and calculations, we came up with, to reduce overall vehicle weight as well as increase the powertrain efficiency, we opted to use in-wheel motors. So basically, an in-wheel motor is a motor that is located within the wheel, and we also use 4 of them. So that is what we are doing at Lighty. We are developing a car from the ground up, and we have to make proper decisions based within our design philosophy. And that's where Motor CAD comes in very useful. So to give you a quick rundown, or I hope this is logically structured so that you can follow, I'll just touch on these 4 points as I go along. And point 4, point 3 are closely related. We will just share about what we are using Motor CAD for at the moment, and then I'll get to that just now. So we need to accelerate, as we said. Like, if you think about upgrading the whole grid, it will take a lot of time and a lot of money. So we can't wait that long. So we already need to accelerate motor design within Lightyear. And as Tim mentioned earlier, Motor CAD has been developed for 20 years, so they've really put in a lot of effort to make sure that the results you get out are accurate, so that you can actually get to a good first pass design to continue in your process. So one of the reasons we need this is to accelerate our design process. And as Tim also mentioned in his presentation, is that the integration of all of these functionalities, the electromagnetic, the thermal, the lab, helps us to run our simulations quickly, get results out so that we can make proper decisions, but also make sure that we get our interfaces correct. So, and then what are we doing it, or what are we using it for? So that's why I'm saying point 3 and point 4 is closely related. So one of the things we would like to see is what are drive cycle efficiencies if you use a certain motor. What will it weigh? Because we obviously, as I said earlier, we want to reduce mass as much as possible and to get to a design. So I hope this gives you a brief overview of why, how, and what. And hopefully the following examples will illustrate a bit more about what we're using it for, and what I and the rest of our team finds helpful within Motor CAD. So today I'm going to present two use cases or things we've used Motor CAD in the past for, but other things we have used it. So just below that, the other use cases is basically to design just the first pass motor, so that you say, this is good enough, let's build this, let's get it out. We have doubled or cross-checked results from a different design. Is it actually as good as people say it is? We've done a thermal design in a different FE package, double-checked it in Motor CAD. We've done different material choices. So say, for example, what if we use a very exotic electromagnetic steel? It costs you a lot of money. If you change it, how does it affect the overall losses in your drive cycle, for example, is one of the things we looked at. Winding optimization, playing around with that is super helpful. And then last but not least, to calculate AC losses, which Tim also touched on in his presentation. So to move on, so a use case for us is for example, when you start out with a great idea, how do you actually make it happen? And one of the things we had to do is to come up with a electromagnetic design, which is part of, so the motor consists obviously of the electromagnetics, the thermal part, the mechanical casing, the integration part of the cables coming in. So there's a lot of interfaces that you need to take care of, but you need to start somewhere. And I'm showing this to show you that you can say you can use the full volume of the rim, or do you use just a little bit. So we had some constraints to work within. So we had a volume to work in and a mass budget to work in. And I'm showing this example because I think it illustrates pretty well what Motor CAD does very well is what Tim also mentioned, is it's got a template-based design, but it makes it super easy to come up with a geometry that you can say, yeah, this looks fine. Or if you want to change your stator slots or your pole pairs, maybe you want to change your base speed. So it's a really, really nice tool to change to get initial design. So basically, this is an example. I drew this in 10 minutes. Please don't use it as a disclaimer. It's just an example of what something looks like. So I just wanted to throw that out there. But the whole idea of what I wanted to say, so we've got a volume and a mass budget within the rim, obviously with a tolerance. So playing around in Motor CAD, I don't know probably if you worked in different, say for example in Maxwell before, or in a different electromagnetic design tool, you will have realized, or what I've realized is it's quite difficult just to get a geometry. It takes a bit of time, and then you still need to get the mass out. So say for example, the mechanical designer would ask me, okay, Chris, you have so much space, how much will it, can you get an electromagnetic design in there, and how much will it weigh? And so what I've done in the past is basically using this tool, or what we've done in the past is to come up with the design based on the volume and the space claim we have. And then and what I want to illustrate with this is, it's an overlooked function. I think it's easy to overlook it, but I think it's super valuable. So actually, you put in a volume, or you come up with the dimensions in the volume, and then you can actually just go 2 tabs. So you start in geometry tab, you go to input tab, you press materials, and then you can get your stator weight, you get your rotor weight, you get your magnet weight or your winding weight, your rotor weight, and your magnet weight. So then you can go back to them and say, okay, this is what I come up. Does this work for you guys? Or do we need to iterate a bit more? So obviously you still have a tolerance on this, but I just wanted to show what I found useful, or what we found useful with Motor CAD. So if you actually have agreed, shook hands on initial design, then you can actually move on. So, and that comes back to the workflow part about Motor CAD. So I think one thing is the parametric design, which is nice, and the quick results that you can get out of it. So now that you have your motor design, or what we did, we had a motor design. So then we could obviously simulate it. And again, this is just an example, so don't use this motor. It's not very good. It's actually terrible. So you can simulate electromagnetic design as you would do in any 2D FE program. But what makes this nice is literally you put that in, you make sure your winding is correct, you run a simulation, and then again, just to illustrate, or what I found helpful, and that's why I'm showing this, is that I hope it's big enough, but from that simulation, what you get out is actually you can get your system efficiency out, which is super helpful, especially if you're designing for efficiency, and you can get your torque out. So say, for example, this torque is too low, you can either obviously increase your current, or you can change your windings to see if you can up the torque. So you can just jump quickly between your winding design or your geometry. You can make your geometry bigger, and then other things that I also find helpful that you can get out of Motor CAD is your torque constant, and obviously your back EMF constant. So what we've done is then, okay, so we have the volume claim, we iterate a bit on the electromagnetic part, and from there we actually move to the thermal part. So what then is nice, and I think Tim also showed it in his presentation, is that you can click and you just transfer your results to the thermal part of Motor CAD, where you can run. You obviously first need to set up your system, but Motor CAD is also being set up because it's template based. A lot of the values are already closely related to manufacturing reliable data. So actually, if you just use a lot of the data within Motor CAD, you can get to a relatively good idea of ballpark where you can end up. So transferring results from electromagnetic to thermal, you can decide, for example, one thing we wanted to check is, do we need to use liquid cooling or air cooling, and how, or do you need to use both? And so basically you transfer results depending on what use case you have. So for example, if you have a rated condition where you want to run it continuously, you export your losses to the thermal part, and then you can run it, say, for example, for an hour. So you run it, you see it goes above your peak temperature, your magnet temperature is too high, you want to make it lower, so you can either increase your fins, or you can increase your flow rate, or both, or your cooling channel. So then you can iterate quickly on your thermal side, and then if you are satisfied with your electromagnetic design, your thermal design, you can move to the virtual laboratory or lab part in Motor CAD. And I don't know, in the past, when I had to simulate efficiency maps, it's quite a bit of work, because you have to run each point and then export the data. And after you exported the data, you need to draw your map, or your efficiency map, or your loss map. So the lab part, which I found very helpful in Motor CAD, is the ease with which you can generate maps, for example. So that's one part of it. And what I'm showing here is that you see on the left-hand side is the efficiency map of this terrible motor I made for this. So please don't use it again. And the dots are the drive cycle. And on the left-hand side, you see, on the left-hand side is the efficiency map, on the right-hand side is a loss map. So that just shows you the total loss map. And what I find helpful is, here you see in this picture specifically, it's the total loss, but you can also look at the magnet loss, the copper loss, the AC copper loss, the DC copper loss, and the iron losses. And then you can see in your drive cycle where it operates most of the time. So and then you can actually run your duty cycle. So you have your first pass design on EM ready, you have your first pass design on thermal ready. Now, if you want to run it in a duty cycle or in a drive cycle, say for example, the WLTP or other one, or your own use case, or you want to run it continuously, what you can then do is, within Motor CAD, is put your vehicle specs in there, and then it calculates the drive cycle for you automatically based on your mass, your aerodynamic properties, if you have a gearbox, all of those parameters needed. And then what you can do is actually you can get out the energy usage, the energy input into your motor. And then obviously from that you can based on your battery size, you can back calculate whether you'd be able to get your range. So these are, just to sum up what I just said, hopefully it was clear, is what I like about Motor CAD is the template-based design, because it helps you to quickly iterate to get to a first pass volume and mass. Then you can actually move on to get your electromagnetic performance. Then you can get your thermal performance, and then in the end you can generate efficiency maps, but you can also run a drive cycle and see what is your actual energy usage. And then just to conclude, what I like about Motor CAD is the workflow, obviously, as I said a lot in the slide. And one thing I will just highlight is the scripting functionality, which I haven't touched on, but that's something I've used quite a bit. So obviously it can get quite mundane by doing the same thing over and over, but as soon as you get the hang of it, you know what you're doing, you can script it easily in Python or in MATLAB or in Excel, so you can use ActiveX. And then looking at time, I will conclude now. So I thank you very much. I hope this has been insightful to learn a bit more about Lightyear and what we're doing and our vision. If you want to find out anything more about us, please check out our website at lightyear.one. And then I would like just to use this opportunity to thank you all for listening. I would like to thank Erna, who's put in a lot of work to make this webinar happen, as well as Edwin and Tim, not only for this webinar, but also for the technical support. They have been super helpful in helping us getting started with the ANSYS Starter program, which I think they will elaborate a bit more on. And that's me. Thank you very much. I hand it over to you again, Erna.
Yes, please.
And thanks a lot.
Thank you very much, Tim, for your time and your presentation so far. As Tim mentioned, there is an ANSYS Starter program. We had contact with Lightyear 3 years ago with this ANSYS Startup. That is also possible. Then, of course, the contact details to look over. Then there's also a possibility, but I will send it when I send the recording, to do a free trial on ANSYS Motor CAD for 30 days. Then, last but not least, are there questions? I will have a look. I see no questions. Are there people who want to ask a question? Hello?
Anna, did you unmute everybody or?
Yes, I unmuted everybody. I will try again. There are no hands out. Okay.
So I think there's one question from Joris.
Okay.
And he asked, in your example, you showed an in-runner design. I assumed Lightyear would utilize an outrunner or actual flux design. Is Motor CAD not containing this? So to answer your question, actually Motor CAD does have an outrunner design, but I think Tim mentioned that you don't have an actual. So I hope that answers your question, Joris. Tim, I don't know if you want to answer these questions.
Yeah, I think the answer you gave is pretty accurate. So
okay.
There's outrunner design, but there's no actual flux. So for the radial flux outer runner, so that's definitely possible in Motor CAD.
Okay, I'm trying. I think that all the attendees are unmuted, I hope.
So actually, there's a few questions here in the question bar.
Yeah.
I'm trying to open it. I'm sorry.
Kijk hoor, let me look. I think a question from Stefan Schlimpert. Oh yeah, he's asking to unmute, but also can we calculate any current break with this? Can you answer on that, Tim?
Yeah, Niels, that depends on what kind of engineering answer you are looking for eddy current brake. But there's definitely generator mode, so that's effectively similar to eddy current brake, if that's the thing you are looking for. But of course, that's you cannot include the other objects. It's only the motor or the generator itself.
Yeah, hopefully this answer was okay, because I think you cannot not talk back, but maybe we
I'm
can.
trying to unmute, but sorry, it doesn't work.
Yeah, maybe we can do it like this. We go to the next question, and if you want to give some additional input, you can put it at the questions remarks. Next question is from also Niels and his colleagues. For Lightyear using Motor CAD, will this be integrated with PLM systems for forces and torques? Can you respond on that, Tim, or maybe also if there are any thoughts from Chris's side? Want kijk, Motor CAD.
I can quickly share.
Yeah.
So I think if I understood the question correctly, is will this integrate with the PLM system? So I'm not sure exactly what you mean with PLM system. I assume it's a product lifecycle management system.
I also think so.
So definitely for the initial design, but there's no, so we not on a concrete, I can't give you a concrete yes or no, but definitely we are using it within our design cycle at the moment. I hope that answers your question.
I know Motor CAD can also be used, what I explained in the first slides, in sort of a digital twin system, where the Motor CAD analysis are sort of a reduced order model, which can be used in there. But I think this is probably more like starting up a Motor CAD within a PLM system.
Yeah.
And then also to store the values you found in that system. So that's a thing we have to come back on, and we will find it out for you. And maybe you can also maybe let us know which PLM system you are referring to, Niels. Next question.
The forces and torques.
Yeah, I believe that's the follow-up question from the eddy current brake. So if you just want to calculate the force and torques of a generator, then that's definitely possible.
Then the next question, is it possible to make an easy design iteration within Motor CAD? Now it seems manual in terms of cooling designs, sizing, yet diameter, etc.
Stefan, maybe I think it will be a great idea if you can just play with it directly yourself. You'll find out how easy it is to just do the iteration within Motor CAD across different modules. So definitely the answer is big yes, but I encourage you to request for the trial to play this by yourself.
Okay, thanks for that. I think you can hear me right now. Huh?
Yes.
Okay, it worked now. Indeed, what I know that it's really easy to change, but sometimes in the early design phase, it's necessary to really iterate over several cooling designs for a certain machine to see what is really the best cooling option. And then specifically, of course, you can also iterate within a certain cooling approach, like for the end windings, certain diameters and so on. But if you can somehow automate this, then that would be, of course, of a benefit. I think it's possible by batch scripting, but I did not try it out yet. But if there's a future option of doing that like via the interface, then that would be nice to know.
Well, because you're changing different type of cooling, so it will require a script to do that. Otherwise, you will have to manually change them, because changing different types of cooling is not one of the let's say, driving parameters. You can definitely change your cooling conditions under a same type of cooling in the interface. Yes. But if you want to go across different types, then you have to use script for that.
Okay, good. Thanks for that. And also thanks for the nice presentation.
Okay, next question. Can we calculate the temperature expansion of the magnetics when mounted on the motor or rotor in function? Question of Niels.
That's a good question. No, it's not possible because the mechanical module in motor CAD is only accounts for the stress that's causing by the rotational force or the high rotation speed. So the thermal expansion is not included in the motor CAD, but you can do that in Maxwell.
Okay. Next
sorry,
question.
Not Maxwell, mechanical. Sorry.
Sorry.
Yeah, in combination with Maxwell. Oh.
Yes. Yes.
Okay. Next question from Jeroen Warmer. Where does RMXpert fit in?
Yeah. So motor CAD is basically a more, let's say, powerful and more comprehensive version of RMXpert, if you like to think of that. So RMXpert gives you the capability to quickly create the geometry template of a motor. So that's the very first part of the motor CAD. But then thereafter, all the simulation and cross multiphysics simulation, that's the strong point of motor CAD. So RMXpert remains a nice tool if you work directly from Maxwell. But if you want to have a early iteration and across multiple physics, then RMXpert is not capable of doing that.
Yeah, I also think MotorCAD is more a practical tool, which is especially created for electrical motor design. And RMXpert is a simple before designing tool, before you really are going to calculate, and especially the practical stuff which is in the MotorCAD makes it also special.
Okay, next question, the last one, I think. It's a 3-day experience PLM system, which I mentioned before. That is what, that's the question as well.
Okay, yeah, we will try to find that out, and
okay.
we'll give you a response on that.
Okay, so regarding to the time, we come back to the other questions with answers by mail. No problem, it's all recording. Thank you all for attending today's webinar, for all your questions and your attention and time. And on behalf of Lightyear, Chris, Infinite, Edwin, Tim, and I, and the whole team, thank you for joining today. Have a great afternoon, and especially of all, stay safe.
Thank you, Anna.
Bye-bye. Thank you all.
Thank you everybody for joining. Bye-bye.
Bye-bye.
Thank you everyone. Bye.
Bye.